Okay, so I already advised that we have been working on a European project with aimed at developing the textile processing technologies where you can develop the textiles from very thin, like 20 micron nitinol filaments, either only the wire mesh or used together with other polymeric filaments. So I can show here, this is just a simple nitinol textile which is woven from shape memory wire, and if we heat it, it does like this. Wonderful. Do you like it? Yeah. So I have the same shot from a Batman movie, which I would like to show it again here. No tak. Cut. I don't have sound. Why I don't have sound? Okay, I need to say what he says. So he asked him, do you have the fabric? If I put a current through it, it becomes stiff and immediately the shape. Yeah. So here he put the current through it and he can do it with nitinol textile. You put the current through it in a fraction of a second, it acquires the shape. You have seen just one bulb like this, but we take the textile, put it on the map of the Czech Republic with the mountains, and so you have this map with the textile. You put it under the stream of current, hot air, and it becomes the shape. Yeah, and the beauty with respect to shape polymer is that with nitinol I can preset the hot shape. Yeah? With shape memory polymers, they always cool, deform, then they have some shape, and heat, the shape disappears. But the shape in the cooling could be any shape. Yeah? In case of shape memory alloy, it's different. I can preset the shape of the textile at high temperature, and when you heat it, it will go to this shape. Yeah? So, sorry, the sound is better than. So again, this is exactly the same thing. Yeah. So we also, it was like 10 years ago. Unfortunately, I don't have this video, but we were on TV with such kind of demonstrator. It was a piece of textile like this, and the guy who was doing this show, he came with the hot water, and it was flat on the plate, and he started to pour the hot water on it, and before the hot water could spill, the textile will close, and you will end up with such kind of ball with hot water, yeah, because it was contained. So it's a very nice demonstrator what these textiles can do. No, but okay, the project was not about the games. This is some kind of more explanation. The project was not about these demonstrators. The project was about the reality, whether we really can develop the textile technologies. There was a lot of problem. First problem was to get the wires from the producers on textile spools in kilometers, because they are very expensive. They are not like the textile filaments, cheap. So then frequently these textile machines, they cannot make 1 square meter. They want to make 10 meter times 50 meters or something like that. So lots of problems, 4 years of very hard working, and we end up with many different knitted or woven textiles. There is, on this slide, there is some kind of demonstration, and so they believe the textiles will be made from superelastic wires somehow. But superelastic wire, when it is in the textile, I mean, when you deform the textile by very large force, okay, they make it strong. You can deform it superelastically, but this is not common. Normally, you have the textile which is bent and straight, or tubular, and such kind of problems. So the nitinol is always deforming in bending or twisting, or you have such kind of snake profile. So we have to understand the behaviors of individual wires inside these textiles. And so you see here like a different kind of textile architecture. And of course, now, if it is made from shape memory wire, what I can do, the same thing, I can load the textile. If I load the textile, I can change this architecture from this one to this one or this one, and expose it to the high temperature, so this will be shape set. This is very good because if you do it, the textile pattern will be perfectly organized, but only after stressing. So this is something like with martensitic variants. Yeah? I load it, I can set it. So now the textile pattern becomes part of the problem. Yeah? So these type of textiles, when they are deformed in such kind of tensile test, they give such kind of curves. So yeah, we were supposed to model them. No, at that time the model was not yet available. We had no idea how to model such kind of curves. But we did the experiments. So for example, the experiments look like this. We start with this pattern. When we deform, this is how the pattern changes upon unloading. So we slowly start to understand. Well, one of the very, very good tests was, if you have the textile, the loading textile in one direction is kind of strange because it will create this type of profile. Yeah? So you do the biaxial stretching. But if you do biaxial stretching, this is also strange because you will have some problems, and sometimes you do more tangent here, more tangent here. So we had the biaxial rig, but we didn't like the biaxial rig. What we like was a bulge tester, so which is here. So we made some kind of pressurized chamber underneath, pressurize it, and there was a piece of rubber on top of it, and we put the textile on it, and when you pressurize it, the textile started to be expanded in biaxial state, and with this we practically did most of the experiment. This is myself. 10 years ago, 15 years ago. What?
You look quite young.
No, just 15 years, no. And yeah, so R-phase, extremely useful in these textiles, because if you have if it's made from R-phase wire, the R-phase gives only this 1%, but if you imagine this 1% strain embedded in a textile, it becomes really very flexible, but put the current through it, it becomes immediately stiff very quickly. Yeah, so you can use this R-phase transformation exactly to make such kind of change of the flexible textile to stiff textile. I mean, not so much that you can fly on it, but definitely in a very interesting way.
So, but stiff, do you mean it becomes like a sheet of metal, or like how stiff it becomes?
No, because this R-phase, then we had to test really the wire exactly. So around in this range of temperature, I have at this temperature, the R-phase transformation starts at some stress, here it starts at 60 degrees, here at 40 degrees, and you have this strain which is about 1%, which is due to the R phase. And so if you touch this, you can deform it in this 1% range if it is in the R phase. But if you heat it up to 100 Celsius, this strains will not be accessible, and it's perfectly stiff. It becomes perfectly stiff. Once you decrease the temperature down to 50, it becomes flexible.
On cooling, B22 R phase is playing the role. Reverse here only. What is the transformation responsible for this?
This is cooling, heating, due to the R phase. The strain is like 0.5%. Here it is like 1%, 0.40.
In application also, only B22 R phase transformation is being used?
Sure. Yeah, well, with this textile, you will never, the beauty is that in the textile, you will never stretch the wire up to 400 megapascal. How you would do it? You would have to pull very much. But if you bend it on the surface, you will have this 1% strain. So actually the R phase is, well, in textile form, I should say generally, all our applications are applications of the R phase, because they affect this bending stiffness very much. If there is R phase, the bending stiffness is low. If there is only austenite at higher temperature, bending stiffness is high, so it becomes flat.
Like
No?
On stress strain curve for like this Nitinol wire, how we can characterize R phase transformation?
Well, I'm sorry. We discussed this before. If I would go back, like R phase transformation, you remember in the stress strain curve, it is you have elastic modulus, and if it's R phase, the modulus is low, or there is some kind of S shape. Yeah. The same upon cooling under stress. It always precedes. You have at first R phase and then monoclinic transformation. So it's called sometimes pre-martensitic transformation. You see it always before. Okay. So this is a demonstration which gives you the opinion how the textile deforms. Yeah. So if you stretch the textile, the wire deforms in such a way. So at first the strains are very small, but then the transformation occurs. So this is the transformation. But in reality, in real textile, you explore these changes. It is clear? Yeah. I mean, if I go again, so now the transformation proceeds in bending only here and here and here. The strains are very low. Now it increases, goes back. So I have some kind of two regimes. Yeah, here the low strain where this can stretch a lot, and then I have here this barrier. This is force. So this barrier, and then some more stress, little bit here. So the question is, can we use this stress strain response in some application? Maybe yes. Yeah, with other wires, you will have here plastic deformation. It will never come back. This object is after unloading perfectly, strain is restored. So the textile strain will be restored.
Resistance you are measuring just with what is stretching, you are seeing voltage drop across.
Yeah, there is resistance. So this is the measurement of the resistance. No, but we don't really interpret it. You see the big change here when the uniaxial transformation occurs. Low current, low voltage. We can observe this resistance change.
Is this work published?
Yeah.
Need to know the parameters.
Yeah, it's in the articles which are mentioned here.
What is the thickness of this wire being tested?
100 micron. Yeah. Now, so well, many yarns in textile are basically springs. Yeah. So this is how the helical spring actually show kind of similar response like the snake. It's all so like due to the design parameter of the spring, you have this. So you see here now the stroke we spoke about is like 50%. So we are approaching the shape memory polymers with 2 strains. We are not limited to 4%. You know, if we use the textiles, we talk about 50% strain, just like in polymers. No, they have 800 strain. Okay, this is one of our. Well, I said we have been working 10 years on that, 2 or 3 projects, 1 patent. So in this is like a textile which was shape set in such a way that into channels we have put inside the tube, and so it was shape set into such form, you know. And so when you have, and this is fabric. This is normally fabric. It was like 1 meter times 5 meters, and so if you put some load on it, I'm not sure if it is here or not. Oh, why it's not here? Oh, okay, I will show it later. Okay. Oh. Yeah, it is here. Okay, so the fabric is here. This is like 5 kilo, and you are heating, and you see. So you can use it like a fire-resistant spacer fabric if you want to make some fire protection somewhere, and so such kind of spacer fabric can. So we have patented it. We have some companies who are interested in it, but so far nothing happened. Yeah, like always. But it is one of the most interesting results of for Arokia. This is a spacer fabric. You know, so in it was shape set in such a way, and then when we put like 5 kilo on top of that, when we are heating it does such kind of spacing, even against the force of like 5 kilo lying on top of a small patch on the fabric. No, so no tak. Okay, so another example, this was a collaboration with several companies. This is a stand graft made of super elastic fibers. So here the nitinol is somehow coiled over here, and the advantage over other medical textile is that at room temperature it will always try to keep this form. So if they deliver it into the human body, it will show such kind of shape. So this is a sort of dream in medical textiles. We have patent for it, but it's with a German company, and I don't have much information what's the fate of this now. The Czech company, which also collaborated on it, also doesn't know much. Okay. Well, there are knitted textiles. Knitted textiles are beautiful, look like this. but the fatigue properties are very bad. So like it's a sort of technology which was developed by this guy Rudy Stallmans in Belgium. He tried his best to introduce it to the medical devices, but failed because of the fatigue problems. Yeah.
These shape settings are done at 500 for 10 minutes same or different setting parameters?
You mean shape setting of what? Of this one? Yeah, 500 Celsius for 10 minutes. He didn't do much, but like the textiles are beautiful. They are really beautiful. The radial resistance very high, excellent. But for stent, one needs to go through this fatigue testing, and it fails very, very quickly because of all these kind of different shapes and frictions and so on in it. So it was a sort of dead end. But otherwise, the knitted textiles are interesting, particularly for making tubes. So tube making with knitting was very successful. Okay, I want to leave the textiles, and in the final 5 minutes, let me talk about the shape setting. So when we have the beauty with nitinol compared to the polymer that we can do this shape setting. In textiles, it was very important. But if you you can do the shape setting with a single wire. If you do it with a single wire, you give it new shape by putting into some mold. But at the same time, you have this surface oxide which grows on the surface, and at the same time, you change it from the cold work state to the functional state. So you imagine now, if you do the shape setting of nitinol, you have to bear all this in mind. So the temperature and time must be set up in such a way that you obtain the shape, you obtain the properties, and you have a good surface. And now, this is the example of some shape setting trials. So I can take a wire which is fully annealed, super elastic NiTi wire which you buy, and then you load it to 400 Celsius, and you heat it up to by Joule heating. So this is here. When this is done,
This is stress, not.
This is stress. This is specific resistance, and this is time. The temperature is missing here, but you are heating between 2.2 and 0.3, and when you do this, the stress goes down and then it goes up. The resistance goes up, it goes down, but this is perfectly linear, and there is no shape set. The wire is the same length. So if the wire is in the austenite and you are heating it, it won't be shape set. So if I take a nitinol wire, very thin wire, like 10 micron, and I try to make a script with 5 centimeter, it will be fully in austenite. You will heat it to 500, you will cool it down, you will put the mandrel out, and the wire will be striped. There will be, if you start with the fully annealed austenitic wire, there will be no shape setting. But if I have cold work wire, so now this is cold work wire. It's not annealed, it has inside a lot of defects. And if I heat it to 500, there is recovery and recrystallization. These defects disappear. So the response here is very different. This is the force, instead of going down, the force goes up and down, and the resistance goes down instead of up. And after this treatment, the wire will be perfectly shape set. So now the shape setting is exactly the same, only in first trial I use austenitic wire which is annealed, which is already super elastic, and this is cold work which is only elastic because lots of deformation, and the result is different. Here there is no shape set, here there is full shape set. So remember this, that if you try to shape set something, you should start with the cold work wire, okay? But to be on the better side, now I have again super elastic nitinol wire, but I heat it to higher temp. I put it into the martensite state. So before it was at 400 megapascal. Now it is at 600 megapascal. This is because I have deformed it to the martensite. So now I have the wire which is I put it on the coil, but at the same time I stretch it so it's fully stretched into the martensite. So there is martensite in the wire. So now I constrain the martensite, and if I do the heat treatment, the response is similar. It goes up, the resistance goes up and down, stress goes up and down, and I got some partial shape set. You know? This is another wire similar thing. So if I have the super elastic wire and I want to shape set it, before shape set it, it's necessary to stretch it to the martensitic, or you can decrease the temperature. At low temperature it's easier to done. But the annealing have to be done in martensite state. The martensite state is the one which gives you the possibility to give it to the new shape. And this is different from steel. In steel you don't care. You just bend it and heat it to high temperature, plasticity will occur and will shape set the spring. But in case of nitinol, you have to be in the martensite. Yeah. It is even so that if I take the wire and because it's localized, you know, so I can stretch it only to 4%. If I stretch it to 7%, it will be completely martensitic like this. Yeah? If it's completely martensitic, I get such kind of perfect shape setting. But now I I strain it only to 4%. Then you heat it, and if you do it, you see you get such kind of hybrid between, because I set only the part which is in martensite will be shape set. So this part will not be affected. This part will be affected. So this is something which, well, I consider very important. For example, if I bend the wire, so if the martensite is localized somewhere, it will be shape set only in places where the wire is. Yeah? So it's like this maybe the treatment of some diseases in the body. Yeah? So the idea is to introduce some material into the human body, and then to irradiate the body, and only the materials there will react. Yeah? So for the cancer it is used, such kind of strategies. So here this is the same strategy used during the shape setting. Only the martensite is sensitive to the shape setting. Austenite is not. Yeah? No. Okay. So yeah, if it's still the same thing, yeah, loading, then heating, cooling. If you do it, the wire will be, after heating, cooling, it will be austenitic, it will be longer 6%, and it will have similar functional properties like this. Yeah? And you can continue this still further on. Okay, so what happens during this low temperature shape setting treatment? But I am afraid I am running out of time, so I will have to skip this. But maybe I can show this one. Of course, we try to look into the microstructure, what is in the microstructure. And in the microstructure there are dislocations and deformation bands. So these are the deformation bands. This was published already about 10 years ago. So they were first twins, austenite 114 twins, which we found in this microstructure. So we realized that the process which occurs in martensite, it creates these twins, and after unloading and cooling, we see them in austenite. So it was the first experimental evidence for this quinking or twinning, that we have found these tooth bands, and so this process is important for the shape setting. But I will, because if I continue to speak more on detail, so on detail in this presentation, you will find some special experiments which were made using X-ray diffraction to analyze this shape setting behavior. You know, it's very, you will find it, you will understand it. There is I can go quickly through it. There is such, I left here such kind of description everywhere for these kind of phenomena, so you will probably easily understand what's going on. And this is at the end. Yeah. So this scheme somehow explains how we understood this shape setting behavior over here. So if you are in the martensite, here the plastic deformation of martensite via quinking is created. You will have these quinks, and this is what we observe in the microstructure. And during this process, we see how the austenite, how the martensite is converted to the austenite. So the experiments give very solid evidence about the process which occurs upon heating. So with this one, I am probably at the end. May I give some few final words now?
Yes, Professor. Actually, during this validity also, you have to give some final words. So
During when?
this validity, just now. We will
Just now.
After this. We have after this.
Okay.
But if you would like to say some future research directions or anything, please go ahead.
Well, maybe I can briefly speak about future research. I would more likely to, first of all, offer all of you who are participants of the course, you can contact me with your problems in future. Maybe I will not respond immediately, but I will record it and I will respond, and I will do my best to help you with specific things. You know. If I should recommend something for new future direction, it doesn't mean if I like something I should recommend it to you. I believe, as now I will say something which is not completely compatible with what I was talking about, yeah, because the request is to say something about some future direction for metallurgists and mechanical engineers, which should be recommended. You know. So when it comes to the alloy development, this proceeds alongside the last 70 years all the time. Now the superelasticity is considered like already well established, and there is some research on nickel-free medical alloy, titanium-based nickel-free alloys, but this is not much exciting. What in my understanding is exciting is the trend to develop the high temperature shape memory alloys. You have seen the ceramics can work around 1000, but ceramics, the responses are very, very limited. Yeah? The beauty of shape memory alloy is that this mechanism, which we utilize around room temperature up to 100 Celsius, can be extended to up to 500 Celsius. So in the last 10 years, everywhere, Japan, Europe, US, India as well, the people have been working on the metallurgists on developing the alloys which can be used at 200 or 300 or 500 Celsius. So it means, first of all, shift the AF temperature to higher temperatures, but at the same time, and equally important, to prevent the dislocation to glide in this material. So, you know, I like these quinks, but in order to have functioning high temperature shape memory alloy, the quinking have to be shifted up to 500 Celsius and 500 megapascal. If it's below, we have a problem. You know? So these alloys are somehow strengthened. The high temperature shape memory alloys are always resistant against dislocation slip. If you suppress the dislocation slip, you can go up to the 200, 300 Celsius. So, like the most successful high temperature shape memory alloy now is nickel titanium hafnium, but it is very brittle alloy, so there is a lot of problems with it, but it already works. There are already actuators which work up to 300 Celsius, and this is strengthened by small precipitates, something like the Ni3 Ti4, Ti4 Ni3, Ni3 Ti4, and but these precipitates contain hafnium. They are different structure, but in the literature you will find how to, so the nickel titanium hafnium alloy always have to be precipitation heat treated around something like 500 Celsius it is. So I would recommend to go, and in India this could be very interesting because you base from such alloys right away, if you have it, it's possible to develop the actuators. And you have here, maybe as I have seen in the lab everywhere, even at Instron, you have high temperature furnaces where you can go to the high temperature. So like the metallurgy can be done here and in many other labs where you are. So there is no and now there is this 3D printing. So when it comes to the actuation, the 3D printing of high temperature nickel titanium hafnium somehow is popular in Japan, USA, UK, everywhere where they develop engines, where they need some actuator into the engines, they work on 3D printing of titanium hafnium alloy. So high temperature, this would be one direction. Another direction would be this high entropy alloys. Basically it is the same direction because only it is not so much based on the nitinol. With high entropy alloys, any kind of alloy which will show martensitic transformation, and these alloys are in principle resistant against dislocation slip, because if you have multiple elements, each of them 20%, the alloy is very difficult medium for propagation of dislocations. So by nature, the dislocation slip is shifted to higher stresses, and then you have the open space for martensitic transformation, and if the alloy can show martensitic transformation, immediately it becomes high temperature, high entropy shape memory alloy. So there is even term now, high entropy shape memory alloy. The term is good because half of the high entropy alloys show martensitic transformations. So this is a very nice area for some kind of metallurgical research. You can easily cast the different kind of alloys and try to investigate them. Okay, then definitely in the applications, the smaller the element is, the better functional properties it has. So any kind of microfibers, thin films, micro elements, micro pumps. This is here for last maybe 20 years, and still many more ideas and developments are coming, and I really believe, well, like one of the major characteristics of nitinol is large power density, which can be utilized in applications. But if the application is some spring big like this, it has many concurrents, many other engines. If it becomes big like 0.1 millimeter, the shape memory mechanism is number one. Nothing can compete with shape memory because nothing can generate this much power and stress and strain like the shape memory effect. Piezo can do it, small strains. All these polymers can do it, low stresses. Yeah? Only the shape memory gives large strain, large stress. So if one makes shape memory film, you can make micro pump, you can make any kind of vibration damper. So working in low dimensions with nitinol is very promising. So for that you need the devices which can deform thin films. So very load cell sensitive to 1 Newton or less. There are no commercial testing machine for thin film, so you have to build your own. So this is a special type of research on such kind of micro electromechanical systems. Not really MEMS, because shape memory technology is not so suitable like piezo maybe for MEMS, but still it is micro electromechanical because you use Joule heating. Joule heating can be used very efficiently in these microstructures. So micro machines is definitely the area of research for engineers with nitinol. Well, the elastocalorics is here like last 5 years. It look like, they have the concept that with loading a nitinol component and unloading, you take the heat out of the environment, you can make refrigerator. They are now already, it has a very powerful cooling coefficient, so lots of energy in one cycle, much more than during magnetocaloric cooling. But the problem is that the SMA element may fracture. So even though more energy is in tension, the element in tension will fracture. So the successful demonstrators now use the shape memory tubes in compression. So if you have tube and deform it in compression, it will not fracture. You can go to millions of cycles, and you can have easily water flowing through the tubes, and you have a big surface. So these demonstrators of elastocaloric cooling based now, as far as I know, they are using the tubes in compression, and they make the tubes by 3D printing. So it's in like a shape with multiple tubes. So elastocaloric cooling is definitely the area which seems to be promising. But it requires a bit time to get into this field. It's not straight away. No.
The compression loading, you were talking about the hydrostatic pressure.
No, just compression. Like it's a stack of tubes and you compress them. They are in contact. They will not bulge. And you prevent the cracking in tension, which destroys the whole element. And the rest is just all about this exchange of the heat and fluids coming through the sample. No, the textiles, it was a bit dead end. I wouldn't say it's exciting, but there are many obstacles which have to be, and it's very expensive. So we had a European project which poured money into this research, but doing it in university based on your own decision is not very good idea. No, and actuators definitely, like as I said, the end of superelasticity is considered like already master technology, and now most of the activity. Even this American SMST society, 70% of if you go to conferences there, even though it started like the Society for Development of Medical Devices, now it is a society for development of actuators together with Boeing and big companies. So the actuators is definitely more promising than superelastic technologies now for research.
Since you are working extensively in wires, is there anybody or you yourself started working in regarding an hafnium or high temperature shape memory alloy wires?
Okay, we have them. We did some experiments, but we don't have any PhD thesis, any project on it. So once I have the project, I would start immediately. We have now a student coming from China with 3D printed nickel titanium hafnium components. So with him we will start, but this will go very slowly because we would have to at first characterize the microstructures. After 3D printing, the microstructures are very complex, so you have to do something about it. You have to heat it. Just again the same story like we spoke day before yesterday.
Is there any applications of sheet metal in NiTi? sheet metal or plates?
Oh, sure. Like in actuators, frequently the sheets are, the strips are better than wires. You know, if you use bending, the sheet is better than wire for bending. You know? So this in robotics, no, people use sheets prior better than wires, and yeah. Well, there are no application of shape memory. I think you know about that. Shape memory is beautiful, but I'm not aware of any single application of shape memory where you would utilize only the without any working against external forces. Once you work against external forces, it is not shape memory. You know, it is actuation. But yeah.
So, excuse, so we will, we will have this valedictory now. So, already almost 1 hour, we thought of starting around 12:15, around 1:15. So, we will try to